My goodness, so many examples. Okay. Let's get here. So,
So, hello everyone. Hope you had a good lunch. We're back for the afternoon of the second day of the workshop. Now we'll have a talk by Julio on geostats.jl, Advanced Geospatial Data Science with Julio. With Julia. Thank you.
that was a good one. It works too, right? Yeah. Wow. Okay, good afternoon, everyone. Let's go for the second talk. So I have some examples that are also run like we did in the previous talk, and a couple of slides as well. I will try to repeat the same format where I will follow the slides, and then at the end I will just show some of these examples running live, so that you can also get this access to these scripts after the talk to run them by yourselves, right? But I want to really like focus on the slides together, and then you can look at all these concepts together, because looking at the same time at code, at slides, at the presenter, and trying to absorb all these things at the same time, it doesn't work. So just go with slides first, then examples, and then we open questions and discussions, right? So Advanced Geospatial Data Science with Julia, and we'll be learning about this framework here called geostats.jl, which is a package that puts this framework into software, right? So let's learn about this a bit more. So what is geospatial data science? So if you try to work with geospatial data, you often have to do a lot of manipulation, processing, visualization, statistical analysis. And if you merge all these things together into an umbrella, that's what we are calling here geospatial data science, right? So it's manipulation, efficient manipulation, statistical analysis, and visualization of geospatial data. I would like to point out that when you call something a framework, it means that it's not just a bunch of disconnected things put together into a bag. It is a way of thinking, right? So you have to really organize how you process and how you manipulate your geospatial data in a very structured, organized way, right? So that's what we call a framework. And this framework is described in a corresponding book that I also share here, and it's materialized in the software. But so a framework is a way of thinking about this geospatial data, how you manipulate it, how you process, how you visualize it. It's not a set of data types in a language. It's more than that, right? What is it not? Also, it's not a one-off, hard to read script. So you see like a lot of data science is done, and you see, depending on the background you have, if you're not a computer scientist or someone that's used to write a lot of code, you end up doing like these one-off scripts that you throw away later because it served for a specific purpose, and then you just rewrite something in the next project and you rewrite it again. We really want to make you learn this framework so that you write very general scripts that you can reuse many, many times with different types of geospatial data and so on and so forth. And also, like, there is this, I don't know if it's true or not, but sometimes, like, there's this culture that, like, data science scripts are slow, they don't run enough at enough speed because they're not written by experts that know their low-level hardware. We also want to take this message out of the table. We want to make you guys able of writing very high-level scripts that run fast. And that's the whole idea behind the Julia language, to make this technology more accessible to non-experts in computer science, but experts in science, right? In geoscience, for example. So before I jump into the geospatial data science problem, which is a problem of, let's say, data manipulation, right? I have this other problem here that I'm bringing to the table. The Julia language has a famous problem called the two-language problem. Here, I'll do a variation of this problem, is the two-team problem, which is basically you have one mindset, which is the software engineering team. And if you read the bullets here, it's basically a summary, a high-level summary of what's going on in the mindset of a software engineering team, right? So you usually write code that's very sophisticated in design. It has very sophisticated design patterns. It has attention to the minor details, right? So you handle all corner cases, performance. You're like really into the code. You have functions that address very low-level tasks. So the software engineering team is usually cares a lot about these minor details, low-level tasks that need to be very, very high performance. But they rarely touch scientific questions, right? Because they're mostly involved with this task of getting the infrastructure for the scientists to then answer the questions, right? So these people, they are, if you put in a pyramid, you have the people at the bottom doing the infrastructure, and the people at the top doing the, let's say, the more high-level science, right? The scientific questions in climate, in earth science, and so on. If you look at this team at the top, the data science team, let's say the scientists that are trying to do science with programming, they have a different mindset, right? So they usually write code with data analysis in mind, right? So they want to do something that has some specific data analysis patterns. They have attention to the big picture. They want to answer the question. They don't care about the minor details or the corner cases of the code, if it's going to break if you feed something that's not valid. And so because they're also handling these high-level tasks, which are like more related to the scientific question, they don't consider too much the hardware, right? So they usually like write scripts, they get their scientific questions addressed, but they're not experts into writing the most performant code to run on a GPU or to run on a multi-core CPU, and so on and so forth. So we call the development mindset in the left the performance-driven development, right, which is focusing on performance and hardware, and the one in the right, the question-driven development, right? So these are two mindsets, two teams, and we really want to try to bridge this gap, which exists, right? It's very well known, with technology, right? So Julia is one of the things that we are really like trying to push over the years and over the years as a technology that bridges the social gap between these teams. Besides the technology itself, it bridges different teams together. So in the specific case of geospatial data science or geospatial processing, right? So we are trying to do this for the geospatial data science community, right? So we created this framework, which is a way of thinking about geospatial data that tries to unite these two words. So there is it was carefully designed to unite these efforts of software engineers with data scientists, right? So you can, as you see some of the examples here in a few minutes, we write very high-level code, but if you need to get more performance, we let the people write new blocks or components that we call transforms and different things in the framework to get more performance. So different people can interact at the same language with the same level of abstraction, and if they need to go low level, they also can. So it was made after years of development, right? So that's not something that started yesterday. We've been developing this for years. I think it's maybe a decade already. I don't know exactly how many years, but it's a long time. And anyone, I think it's one of our personal goals here in our agenda is anyone with basic programming skills that can read high-level Julia code, high-level Python code, can potentially become a contributor, right? Because it's 100% Julia. We don't access very low-level memory patterns and buffers and all these things. We really write everything in Julia, and it's usually easy to understand. So we want to keep it that way. There's lots of work to do still because, of course, we're a small team. There's not many people working on this. We hope to get more and more contributors over the years, but because of the small team, we cannot handle all corner cases, right? So sometimes in a corner case, things won't be as fast as they could. So we ask help for people. So, hey, this is not working with the speed I want. Submit a contribution. We are happy with this, but I'm just setting expectations here because sometimes you probably load a very big data set and things are not as fast as you imagine. So that's probably because no one optimized the block that you are trying to use, right? And I think the main resource to learn this is the book, right? So I will cover in this talk today one chapter of the book, but the book is open access. I already shared in the previous talk. It's online. You can Google for Geospatial Data Science with Julia, and it will show you the URL that you can access all the chapters that are already available. So as I mentioned, like the topic of this specific talk here is one chapter of the book, which is about lazy pipelines of geospatial transforms. I will undo all this fancy vocabulary and explain what this means. But basically, we'll be able to take a geospatial data set and convert it, process it into different geospatial data sets. And if you follow the previous talk, this geospatial data set will be a geotable. You get this geotable, will feed into a sequence of transformations and get a geotable at the end. That's the whole idea. So what's the geotable? Very quick recap from the previous talk. A geotable is this attempt to arrive at a universal representation of geospatial data that generalizes all types of domains that you encounter in science, right? So raster, vector data, 3D unstructured meshes in physics and climate models, etc. It behaves like a table, but it's useful for statistical analysis. We design a bunch of features in this table to handle statistical analysis code, right? So we've seen some of this before, like it knows about scientific types, categorical, continuous types. It knows about units, right? So if it's in meters, in kilograms, all these things are useful for the data science test that you need to do. And it's made of two things, the values and the domain, right? So I think the most important bit of this review here is you need to remember that a geotable is made of a table of values and a domain, which is stored in the geometry column. So these two names here will be used in the next slides. The values of the table is the geotable is the table of measurements, and the domain of the geotable is the physical domain, right? So I'm illustrating in the right here one such domain. So let's talk about these pipelines of geospatial transforms, what they are. There is this sentence here at the bottom, right? So they're powerful manipulation and processing of geotables, but what that means exactly we'll see now. So before we jump into these examples, let's categorize these transforms into three main kinds. There's feature transforms. These are ones that consume your values. For example, you have your geotable, you look at the values or just the measurements, you operate on these values and you return a new geotable. Geometric transforms, on the other hand, they operate on the domain of the geotable, right? So you have your geotable, you concentrate on the domain, you operate on this domain, rotating the physical region, stretching it, doing something with the physical domain, and returning a new geotable. And there's this more general class, the geospatial transforms, which is a mix of the two. It can both take the values and the domain at the same time, do some operation that involves the two, and return a new geotable. So these are the three classes that you're going to cover here. So feature transforms, right? So as I mentioned, a feature transform is just like a function that takes the values of the geotable and produces a new set of values over the same geospatial domain. We divide this feature transforms into 3 subclasses: basic, cleaning, and statistical, and these are the same ones that are described in the book. So what I'll do here, I will switch to the VS Code again, as I did in the other talk, and I'll show some examples of what these feature transforms are. I don't know if the font is too small or it's too big, but hopefully you can see something. If you don't, maybe you can access the link on YouTube, right, for the live stream. But here what I'm doing, I'm loading the framework, which is this main module here, geostats. It reloads every single thing you need to do for geospatial data science, including the geotables package we've seen in the other talk. I'm also loading Maki, which is the previous presentation we saw from Simon, right? So I'm loading the GL Maki backend that Simon presented in the previous talk before lunch. And what I will do here, I will start creating a example geotable, right? So what I'll do, I'll create N, capital N samples, in this case 10,000, samples with 4 columns. So I would say variable A is made of these values, variable B is made of these values, C and D. I'll place all these columns into a named tuple, which is one of the built-in table types we've seen in the other talk. That's a valid table in Julia. And then I'll georeference this table on a domain. In this case here, I'm using a Cartesian grid with 100 by 100 pixels, right? 100 by 100 quadrangles. So if I execute this code, you see here in the right, let me hide the files to get more space and execute it again. Oh, sorry. Switch to what? Sorry, Alex?
It's just the YouTube screen that's like this.
Oh, so it's not on me. I think it's on the people organizing the... because I'm already sharing there. So the slides are... my screen is not showing apparently in the YouTube stream. Is it? It's okay? Perfect. Perfect. Oh, got it. But you guys get it now on the stream, right? Okay. Perfect. I just need a confirmation. If it's already on the stream, I can continue. It's on the screen? Awesome, awesome. So what you're seeing here, let me just repeat this part because some people online may not have seen, right? So I'm loading the main package here, geostats.jl, which is the package that reloads the whole stack. And that will be the only thing you need to import if you are wanting to do geospatial data science in Julia, right? So if you import this package, you can also import the GL Maki package, which is one of the backends that Simon presented in the previous talk. And in the second cell here, what I'm doing is I'm creating a geotable, an example geotable. So I create 10,000 samples. I create 4 synthetic columns, right? So variables A, B, C, D. And I choose a specific distribution of these columns we'll see soon. I place these columns into a named tuple, which is a valid table type in Julia. And then I georeference this table into a Cartesian grid. That's the domain, right? So if you do this, you'll see here in the right, in the terminal, there are 4 columns with features, the values of the geotable, A, B, C, D. And there's an extra column here with the geometry. I should probably reduce this even further so that you can see. Let me run it again. It's still not possible because the screen is so small here. Let me try it again. Okay. Now at least you can see the header here, the geometry, right? So you have 4 features in the values of the geotable, and you have the domain here represented as the geometry column. Now say I want to visualize what is in it in this geotable, right? So I can load, for example, one package that's very, very useful is pair plots. Pair plots is useful for multivariate analysis, so it can take any table in Julia and produce these plots called corner plots or pair plots. In order to do this, what we'll do, we'll take our geotable, I'll extract just the values, just the subtable with features, and I'll send it to the pair plot. So if I run this here, you should see a plot opening up here on my other screen. Oh, it's not going to be full screen. Yeah, I should probably, the resolution of my tablet's not allowing you to see everything, but you can see there are 4 variables, A, B, C, D, and if you plot these variables together, you see this multivariate distribution, right? So you see these shapes with 2 modes and these elliptical shapes because some variables are Gaussian, some variables are multimodal, but this is just an example data set that we use an example as to run some of these transforms, right? So this is a random geotable. Another way that I would like to show you that really, let's say, streamlines the syntax and makes the scripts very readable is use the Julia pipe operator. So you see this beautiful arrow here in VS Code. That's something that VS Code does, but you can get this symbol by pressing vertical bar. My keyboard was misconfigured, sorry. 1 second. It's in Portuguese, I want it in English, okay? So if you say vertical bar and then you write greater than, Julia, the VS Code editor will just merge the two into this beautiful arrow. And then if you use this arrow, Julia will just feed what's in the left of the arrow to the right and continue doing this. So I'm feeding the geotable to the values function to extract the features, then feeding the result to the per plot. So it's equivalent to this line here. I'm just showing this because we'll be using this a lot in the next examples, right? So let me just execute this code here so that you see it works the same. So it generated the same figure we've seen before, right? So I'm sending the geotable to the values to extract the features. Then I'm sending it to the per plot function to generate the per plot. Now let's do some basic feature transforms. So what would be the most basic transform you can do with a geotable? Most of the time you need to select a subset of variables for your analysis, right? Sometimes you have tens of variables and your analysis only depends on a subset of these variables. One such transform is the selection, right? So you say, send my geotable to the select of A and B. If I run this code here, as you see, it will just take the two features that you care about. So it is going to discard C and D, retain A and B, and the geometry column. So everything retains the geospatial information. It's never lost. I can also say, just return the 3 first features, right? So I can just take this geotable and extract ABC. And there are very fancy selectors we call, right? So you can use a regular expression that says, return all the columns that have B, C, or D in their names, right? So I can just do this and it will just take the features of interest. I can also select and rename at the same time. So these are all examples that you can find here in the book. I'll share the script later. You can select column A and rename it to capital A. Select column B, rename it to capital B. What it will do is it will do the same as the selection, but it will also rename. You see now that the columns have capital A and B. Or you can also do the, let's say, the opposite operation, which is reject. Instead of select, you can reject columns. So I can reject the feature B and retain A, C, D. I can select A and send it to the viewer. Remember, in the previous talk, we saw ways of visualizing geotables, right? So if you select a feature and send it to the viewer, it will just create the visualization of the variable you care quickly, right? So you don't need to write a lot of code to just quickly inspect what you want to see, right? So here, I selected variable A, send it to the viewer, and now you have this grid with this random distribution that I created, right? So it's a Mackie visualization with the interactions that Mackie supports, and it's very convenient for quick exploration. Now let's go to another example of basic feature transform, rename. So instead of selecting and renaming, you can just rename columns. That retains all the other columns without dropping them out, right? So I can rename A by capital A, B by capital B. It will still retain column C and D because I'm just renaming, I'm not selecting, right? So you see now that A and B are renamed and C and D are retained. You can do a function on each of these columns of interest or in all columns. So there's this functional transform. So I will do here, I will send the geotable to the functional that applies the cosine function over all the values. And then I extract the values and send it to the per plot. So you see now that the multivariate distribution has changed, right? So if I show here the multivariate distribution of this geotable, it has a different multivariate distribution produced by the cosine function on the original multivariate distribution. Another very useful basic transform, these are all basic data manipulation, right? So you probably can do all these things in many different ways, in many different languages. What we've tried to do here is a set of transforms that's abstract and data independent, so that you can express yourself just in terms of these transforms and then feed later any geotable that you have. So the map, the rename, the select, and all this, they are pretty much like independent of the data. You express what you want to do, and then you feed the data later. I'll show examples of this moving forward. But the map here, what it does, it takes the column A, applies the psi function, takes the column B, applies the cosine function, and renames the result to cosine of B, right? So if we just execute the cell here, you see that it retains the original columns, A, B, C, D, but it creates a new column, A underscore sine, because I didn't provide a column name, and it creates a new column, cosine of B, which is applying the cosine to the column B and renaming the result to cosine of B. There are many other ways of selecting columns as well, right? So you can do map of columns 2 and 3, and then you get a function that takes the two values of the columns, right? So a value of B and a value of C, return an expression, and it will apply this expression to this selection and return a column that I'm naming here as f of BC. So this is another example. And to finish this set of basic feature transforms, we have the filter, which is also very useful. It's filtering some of the rows of the geotable based on some predicate function. So I can say filter all the rows for which the value of A is smaller than 0 and the value of B is greater than 0, for example. And if I just execute this, you'll see that it will return this geotable over this subset, right? So here I'm taking the result, and you see that it's less rows than the original geotable, right? Oh, I'm executing a bunch of random code here from another script, so let me just clean here. Okay, so if you execute here this again, you see the result. And the other one that I would just like to point out here is sorting, right? So you can just sort the rows of a geotable based on columns of your interest. And there are many keyword arguments that you can pass to all these transforms. They're all documented in their respective doc streams. What's another very common operation that you need to do in data science? Sometimes you get a data set that comes out of raw sensors, raw measurements, and the variable names are terrible. Like, I mean, I don't understand why, but every device chooses a very weird variable name. It is never readable to a human, right? It's always very garbage, underscore, hash. It's very complicated. So data science starts with like clean the data as much as you can, filter all the things that you don't care, and then start your analysis. So cleaning transforms are very useful. One of them is, for example, the selection and renaming of these variable names, right? So for example, here, I will create a geotable with very weird names. So here is a geotable with a column called, a variable called ABCD-F and another column called B underscore 2 parentheses 1. So this is like random names that could come out of a device or something like this. Now I want to standardize these names because, I mean, as a human, I want to process and report results in more readable names. So there's this transform called SDD names, where you send the geotable there, and it will just like try to convert these names into a standard. There are many supported standards. The default one, I guess, is uppercase separated by underscores, but you have all these standards, for example, upper camel. And then you say, okay, I prefer to use upper camel. I prefer to use upper flat. And it will just rename the variables to a standard that you are more happy with. And you have all this documented as well in the doc strings. Another very useful cleaning operation is replace, right? So sometimes you have geospatial data or geotables, like this one here at the bottom with missing values, for example, none, right? Not the number, or missing, or negative 999, because that's not a valid value for that variable. For example, it's a porosity or permeability or something that cannot be negative. They usually use a negative value to signal that this is a invalid measurement. So one thing that you can do is replace all these symbols on the geotable with the replace transform, right? So you can say replace negative 999 by missing, and none by missing, right? So what we'll do is just like do this replacement for you. And the missing is a special value in Julia for missingness, because this is a very scientifically driven language, right? So they have a built-in type for missing from statistics, and so you usually want to convert all these low-level representations to something that's for sure missing, because that has a type that Julia understands and will allow you to do more fancy stuff with these missing values. Another way that you can replace values is by providing a predicate function. So in Julia, when you type smaller than 0, for example, it creates a function that takes 0 and something else and returns the result of 0 is smaller than something else. Right? So what I'm doing here is I'm saying replace anything that's smaller than 0 by missing. Right? So that's one way of performing this replacement. But you can feed in here any predicate function that returns true or false depending on a condition to replace the value. So I replaced the minus 999 by missing, but I left the num untouched. Another operation that's very useful, which is similar to replacing missing values, is the coalesce transform. The main difference here is that coalesce will also change the column type. So if you replace missing by a number, in Julia everything is typed by the compiler, right? So if you create a table that has a column of 1, 2, 3 missing, the column type of this table will be a union of missing and float, for example. If you want to make sure that no missing value can be stored in the future, you coalesce this table so that it removes the missing and puts something else there, but also changes the column type to be just a column of float. And that's more restrictive and important sometimes, so that you make sure that your script never reintroduces missing values, right? So if I say here the type of the column A, it will be just a vector of int. Whereas if you have used replace the missing by something else, the column type will still be a union of missing and something else. Another very common one is drop missing, right? So I should have scrolled here actually. So the coalesce, I just coalesce with the value 2, right? So to replace missing by 2. But you can also drop the missing, right? So you can just feed this geotable into the drop missing transform, and it will just drop all the rows that have missing values in all variables. And you can also select specific columns of your interest. So let me just get back here to the deck of slides, because maybe I'm close to the time here. So let me get back. No, yeah, I'll proceed with just a few more here. So the final one that is still considered a feature transform is statistical, right? So if you look at a lot of these statistical transforms, for example, principal component analysis, factor analysis, I don't know, sampling the geotable in specific locations, or centering the distribution, or calculating the z-score, all these statistical transforms can be performed. They're also considered feature transforms. And so here I would just sample, for example, a subset of 1,000 pixels, right? So here, if you look at the code, I say, hey, I have a geotable which is over a grid. It's a raster. I will sample 1,000 of these measurements, which actually corresponds to 1,000 quadrangles, without replacement. After I do the sample, I just send it to the viewer, and you see that it produced that figure here, right? So it automatically changed the domain from a grid to a view of a grid and send it to the viewer. So you see here now that you have a collection of random pixels selected with this transform. You can also describe here a transform, right, to get some basic stats like mean, describe a geotable to get the mean, minimum, median, and other summary statistics. But you can also send it to the center. For example, center variable A so that it has 0 mean, and you'll send it to the describe function again, and you'll see that the mean now is 0, right? So it's 10 to the minus 16, right? So it's effectively 0. There are many other similar ones like mean max. Instead of centering, I just scale by the mean max values of the columns. I can compute the z-score and so on. These are very similar. And the STD feature fits transform just tries to standardize all columns regardless of their scientific type. If it's continuous, it will probably use I don't know if it's the z-score or if it's the mean max. And if it's categorical, it will leave the column as is, and it does something differently depending on the scientific type of the column. There are many more here. For example, the quantile transform will take your multivariate distribution and take each variable and convert to a different distribution from the distributions package, right? So I can send my multivariate distribution to the quantile, and by default, it's the normal distribution. And if I send it to the pair plot, you'll see that all those multi-modes that you see in the original data set are gone, right? So there are the two modes that we had here kind of collapsed into one because we are trying to get each of these dimensions, A, B, C, and D, convert into a Gaussian. And when you plot them together again, you lose some of these multi-modes, right? So that's the idea. So there are more here, coerce and others that are also very convenient for people working in machine learning and all these areas, right? So for example, if I create here a geotable, let me create here this ST geotable. This ST geotable in the example, it has a column A, which is categorical, and a column B, which is continuous, right? So what you can do with categorical columns is many things. So you can do, for example, change the levels of the categorical array, right? So you say, I have a vector of categories A, B, C, D, but in my data set specifically, only A, B, and C appeared. So if you want to increase the number of labels, you use this level. So I'm increasing here to have levels 1, 2, 3, 4, right? That's something that is done internally so that you can do correct classification with the correct labels. You can also do a one-hot transformation, which is very useful when you're handling these neural net-based models, which handle these 0-1 arrays as indicator functions, right? So if you go one hot here, one hot of A will take the column A, which is made of 1, 2, 3, and you split it out into 4 columns for each of the levels, right? Because I set the levels from 1, 2, 3 to 1, 2, 3, 4. I have 4 levels now for this categorical array, and it breaks the 4 levels of variable A into 4 columns of zeros and ones. And that's very useful sometimes because you need to train a model that expects arrays of zeros and ones. There's also this indicator transform. It takes a continuous variable and creates categories, splitting into different subintervals. So you can split into a linear scale or a quantile scale. It's also very useful sometimes. So you get here column B. I split it into 3 intervals. Sometimes you have continuous data that you need to quantize, and that's what this indicator does. And basically that is the set of feature transforms that are explained in this example. There are more in the framework and more in the book also. So let's get back here and move to the second set of transforms. There are many of them. As I'm explaining here, this is one chapter of the book, right? So transforms is so many things that we don't have time to cover all the stuff here, but just the transforms will be something to know. But geometric transforms, do you have a question, Sebastian?
Yeah, to the what you just talked about just now. When you want to do machine learning or deep learning with geospatial data, it's often very annoying to make a correct distribution, both in terms of geographical location and whatnot. Is that also easy to do with the view tables?
You mean like converting the features into this?
Make sure that in my training set and in my validation and testing set, I have specific type of geographical locations and
doing splits geographically, right? So yeah, we have partition methods as well, like they're more low level, you have access to them. So when you do, like for example, a group by variable, that's one type of partition that's kind of non-spatial, but you also have other kinds of partition that work with, I want to partition this data set by a vertical plane. I want to split this data set by different spheres that don't overlap. There are so many different partition methods implemented you can look up and can discuss later. But you can take a geotable and split into test validation that are geographically split, right? So that's also possible. So geometric transforms here are the ones that operate not on the features, but on the domain, right? So you take a geotable, you want now to transform the domain or the geometry column. These are the ones that take the geometry and produce a new geometry column in a way that's not materializing the geometries, right? So it's smarter than that. And we can divide these geometric transforms into 2 types as well, coordinate transforms and advanced ones. I call it advanced because I couldn't find a better name, but coordinate ones are the easiest ones to understand, and there are ones that are most popular in geospatial work. So if you go here and you load the GeoIO package as we did in the previous talk, I will load this Beethoven model, which is just a geospatial table, right? So I can load this guy and visualize it here. So you see that this is a geotable of a statue of Beethoven, or someone may be interested in modeling and doing geospatial data science with statues. I don't know, someone may have this kind of application, right? And suppose that I want to perform transformations to this domain, right? So you see that if I execute this code, let me execute it again. The Beethoven statues is kind of laying down, right? So it's like sleeping right now. How do I rotate it so that it's looking to the scene, right? So I can, for example, take this geotable and send it to a rotate transform where I specify different rotation specifications. We support all rotations from the package rotations.jl, one of which is use rotate by analogy. There are many ways of specifying rotations, quaternions, Euler angles, all these different kinds of specifications that are supported. But one that I find very useful is rotation by analogy, which means if you know how to rotate a specific vector to some other position of your desire, right, you can just use this pair of vectors as analogy for the rotation you want to make. So for example, I don't know exactly how to represent this as a quaternion, but I know that I want to rotate vector 0, 1, 0 to the position 0, 0, 1. So I can pass vector 0, 1, 0 to 0, 0, 1 that specifies that that's the rotation I want to make by example. So if I rotate this Beethoven here, you'll see that it's now, let me just visualize it again, sorry. If I visualize it again, it will now be looking to the back wall, right? So I rotated it because I rotated by analogy 0, 1, 0 to 0, 0, 1. Now I'll rotate it once again. I'll move the vector 1, 0, 0 to the vector -1, 1, 0 so that it faces the camera, right? So if I run this again, now it's facing myself. And all the attributes that are associated with the geotable are still there, right? So I'm just operating on the geometry column, but everything that's related to the measurements that are made are still there. They're not thrown away. And you can also rotate 2D data sets. For example, if you remember, we have our GT geotable, which is over a grid, right? So I can take that geotable and rotate by a 2D angle of pi/4. And if I send this to the viewer, you see that it's just like a rotated raster, right? So it's like you have your grid. I'm just wanting to rotate this grid. It will do this in a very smart way, right? It's just going to represent this as a rotated grid without any allocation of memory. But now in the time that it plots, it just calls the appropriate Mackie function to plot a rotated image. You can also translate, and these are basic affine transformations like rotate, translate, stretch, which is basically like moving your domain in basic ways. You can also standardize the coordinates. Sometimes, for example, you want to train a model or you want to do some processing. And if you use the original coordinates that are very big numbers, I don't know, you are using something that has, I don't know, UTM coordinates or longitude, latitude, whatever scale you're using, sometimes doing operations on these big numbers can lead to numerical issues, right? So it's sometimes good practice to just standardize everything to between -1 and 1 or minus small numbers, right? So the standard coordinates will just do this. We'll just take your grid and squish it into a box of size 1 by 1. Sorry, let me get back here. So now let's go to the advanced geometric ones. So advanced geometric transforms are basically the ones that don't fit in the category of coordinate transforms. So what is a coordinate transform? A coordinate transform is one that takes point by point in your domain and applies the transform on each of these points. So it takes all the coordinates independently and applies it in parallel, right? Transform, translate, rotate. The advanced ones are ones that actually sometimes manipulate the topology of the domain. What we call topology is like how these quadrangles are connected to each other, how these geometries are connected. So here, for example, I'll create a polygon with 2 holes. So if I show here, it's just like a polygon with 2 holes in it. One transform that does this change in topology is called the bridge. If you do a bridge on the polygon and you specify this epsilon here, it will just connect all the holes into the outside exterior and make it a polygon without holes. So it's like, it's a very nice trick for people that work on geometric processing because changing the connectivity like this you now have a polygon that you can process, assuming that it doesn't have holes. Do your operation, then undo the transform to get the holes back. So we do this, for example, to do some discretization of complicated geometries with holes, right? So you see here that the holes were connected by these bridges, these small gaps, and I can specify the epsilon to do this creation of bridges. So this is one that's not a coordinate transform because it changes the number of vertices in your polygon, right? So I introduced 2 new vertices for each of these bridges inside and outside, right? So it's a different transformation. There are other ones that are coming from computer graphics and geometric processing communities. For example, the Taubing smoothing one is one that takes your surface and tries to smooth it out to remove some artifacts. Sometimes you get noisy surfaces, and you want to just cut out all those weird peaks. So, for example, take the Beethoven model, and I can create this new figure with the original and the old Beethoven, right? So if I zoom here, that's my original domain, my original geotable, and you see it has a lot of detail, right? So I can zoom in here so that you see all the sharp corners. But the one that I smoothed with Taubing smoothing, it became more blur, that's the effect of the Taubing smoothing transform. So it can be useful, for example, again, if you get raw data that's like a surface, but it's all made of this weird peaks, sometimes you can smooth it out before you start doing your analysis because you can have better results like this. So let's go now to the last set of transform, which is the geospatial one. It's a set of examples so that you get used, but these are all covered in the book. Geospatial transforms, these are the ones that consume both the values and the domain of the geotable and produce a new geotable with these 2 potentially modified, right? So these are very common when you're doing geostatistical work because one thing that geostatistics does that statistics doesn't is it consumes the domain and the values at the same time, right? So sometimes I need to remove a spatial trend. So that's like kind of feeding a polynomial in space, removing that trend and working on the residual process, for example. Or sometimes I want to convert the information that's in polygons and rasterize it into pixels because that will align with the features that I have from satellite so that I can train a machine learning model. These are all examples that involve both the domain and the features. And you can have examples of this like this one here. So I'll create a new geotable, which is just a random one again. And you see it's like a quadratic function plus noise, right? So I'm just saying, here I have a variable z over a grid, a quadratic function plus noise, and I just want to remove this quadratic trend, right? So because I only interested in studying the residual variations here. The quadratic behavior is known or is physical. I already understand it. I want to understand what's left. So I can just detrend with a polynomial degree 2, 3, or any degree and send it to the viewer. So if you do this, you'll see here that it removed the quadratic trend and just retained the residual process, right? So this, oops, I'm out of time. And then you see that this is one example. Another example, for example, if I load this data set, which is an image, right? So it's an image, a PNG image of 2 letters. There's a letter A and a letter B in this image. If you do this pod trace transform, this is a polygon tracing, it takes this image, which is a raster, let's say, and it looks on all the pixels to find out what are the polygons for each of these different colors, right? So if I run this pod trace transform, it will convert, as you see here, in a few seconds, hopefully. You see that the original domain here is a transformed grid, is a rotated grid somehow, with quadrangle geometries. And after the pod trace is finished, which is still running on my tablet, let's see. Yeah, I wish I had a more powerful laptop. Let's see if it's going to finish. Okay, so you see like the original domain was a grid of quadrangles, and the resulting domain was a geometry set of multi-polygons. Right? So I have letter A and letter B in this, and if I visualize the second geometry on this new geotable, it will correspond to the letters because the letters are in color black, right? So this is a new domain made of letter A and B together, and this new domain is made of sub-polygons, but now this data set is vector data, right? So that's a way of converting between raster and vector, And the opposite operation or transform is called the rasterize. So I can just create this geotable over this polygon. So this is vector data now. I have the variables assigned to these polygons. I now want to rasterize. I can just send this polygon geotable to the rasterize of 20 by 20. So I want to convert into a raster of 20 by 20 pixels. And it will just create this new geotable with a grid geometry which approximates the polygons, right? So this is also very common to do, and it's considered a geospatial transform because it takes the values and copies to the corresponding pixels. It also operates on the domain, and it's a more evolved operation, right? Now I want to move to the more final, and I think I have a few minutes left, but you can look it up later. It's one of the most powerful features is pipelines. So we've seen how we apply transforms independently, right? 1, 2, 3, you can just feed one after the other. But that is not what we usually do in data science. We want to create a full pipeline that's independent of the data, and then we want to feed one geotable once to this pipeline and let it do all the operations for you. So I won't have enough time to explain, but the main idea here is we've been using Julia's pipe operator to send the geotable to transforms. Right? So this is vertical bar greater than. We replace this operator by two new operators that are provided in this framework, this arrow, which you get with \to, \2, and this square union here, which is disjoint union. It's \sq cup. I also explained this in the book. But so if you go here and you create pipelines, what is the effect of a pipeline? So for example, I can take a transform that selects columns A, B, and C, and send just these 3 columns to the quantile, right? So I create a pipeline here. You see that this is a pipeline object. It doesn't involve any geotable. I can then send the geotable to the pipeline, and you just execute the 2 operations one after the other. I can create trivial pipelines, and you see that like there are optimizations happening behind the scenes. So if I take a pipeline and attach to it an identity transform, it doesn't do anything. So if you add an identity to any part of a pipeline, it will just be ignored because it's like nothing to be done, right? So it has these kinds of optimizations, and you can do things in parallel, right? So if you construct a pipeline with the other operator, the disjoint union, for example, I create pipeline 1, select column A, and run the indicator transform to create 3 categories of this continuous variable that will execute here as a new geotable, right? I can also create pipeline 2 that takes columns B, C, and D and runs PCA, right? That creates another geotable. But instead of doing this step by step, I could just create one pipeline, the pipeline that takes pipeline 1, this joint union with pipeline 2 that creates a parallel pipeline. As you see here, it's represented by 2 sub-pipelines of sequential transforms. And I can just feed my data to this whole pipeline with parallel branches, and we try to parallelize things as much as possible. So there are always room for improvements, and please feel free to join in the code and see if there are more parallelization opportunities there. But you see, like, if I just feed one geotable to this pipeline, it will take column A, it will break into 3 indicator functions, apply the quantile, that's these 3 columns. It will take column B and apply B, C, and D, and apply PCA and return these 2 PC components. So you can quickly build very complicated pipelines, and they work with grids, with vector data, with unstructured meshes, with everything in the same syntax. So the idea is that you create these pipelines and reuse them after. So let me just finish here. These concepts of reversibility, geospatial split, apply, combine, geospatial joins, they're all covered in the book. They're not covered here. We just covered the concept of transforms. But you have total access, as I mentioned, if you just Google geospatial data science with Julia to get access to these other concepts. And if you want to get involved, again, like the purpose, I think one of the purposes of being in a workshop is being present with the person, right? So come say hi. I'm here the whole week. I'll be happy to brainstorm ideas. The book is the best resource to get more involved because you know what's the message behind the framework. If you want to, or you believe that this is a good effort, like give us a star on GitHub, share on social media. It really helps because the community is small, so any help is valid. If you want to get support from our open source community, right? So there's a Zulip channel where you can join, #geostats.gl, and you can contact me as well if you need something more dedicated, right? So we are open for that as well. if you have questions, I don't know if you have time, please feel free to ask. Thank you very much.
I really like this pipelining. I find it a very beautiful way of thinking about an operation but not yet applying it. I was wondering how is the, so you mentioned you implemented the two operator, and how is because Julia has this circle for plotting functions, right?
Yes.
How is that different?
So the composition in Julia, like the circle you mentioned, is eager, right? So it's eager evaluation. So if you compose a function like this, it executes the function 1, gets the result, and apply function 2 to the result of function 1. So it's like applying functions and getting the intermediate results generated, right? What we're trying to do here with pipelines is lazy evaluation in the sense that we build the pipeline and try to do some extra optimizations in the pipeline level before we send it the geotable to it. So the main difference is like compositions in Julia with the circ, \circ, or the Julia's pipe operator, they're eager evaluation, and we are trying to be more lazy with the two operators we created.
Okay, so it's more like a performance thing than like conceptual difference.
Also, I think it would be not just performance, but I think expressivity maybe too. I don't know, because because the circ is only the sequential one, right? So if you use the circ composition, you apply one transform after the other. The other operator that I provided, the disjoint union, allows you to create branches that operate in parallel. So you get one single geotable in, you branch, and you create many geotables that join at the end into a final result. That's not possible with just the circ operator.
Yeah, and then just related to that, so the individual elements of the pipeline usually create, I guess they're actually functions, right?
There are structs, there are types.
They're types. But then sending it to the pipe, I have to define some kind of like a functor to it? So
Exactly.
Okay.
They're functor structs, exactly. That's the design pattern.
Okay, so something like this, whenever you said like replace, for example, that's why you write it with a capital R, because it actually creates that, at the moment you call it, it creates a struct.
Exactly.
Which has a function attached to it, and so you can publish it.
Exactly.
Yeah, very nice.
Mm-hmm. That's all?
Okay.
Awesome.
Thank you, Julie.
Thank you.
Julie, not Julia.
That was a cool one. Go here. Just take this part. That's yours.
Okay.
So many things, sir.
Yeah, don't worry. Yeah, it's down here. Okay. And your it's our
That's
laptop.
yours.
Okay. Okay. You have. So now we'll have the second hands-on session of the day, entitled of Vessel Detection by Mr. Christian Sorensen. And Christian earned his master's in Earth and Space Physics and Engineering from the National Space Institute of Denmark in 2021, with a specialization on Earth observation. Following his master's, he pursued a PhD at DTU Security, from where he worked to enhance maritime domain awareness and surveillance through the integration of satellite data and AI. His academic journey also included research in Canada, Korea, and Norway. Currently, he's channeling his expertise into a startup venture. His research primarily revolves around the fusion of satellite data, including synthetic aperture radar image and AIS data for maritime surveillance, and the development of predictive models, for example, trajectories. Thank you very much, Christian.
Thank you.
Great.
course. Everything's amazing. So yesterday, Ms. Eugenia Nunes gave us a really good presentation about a bunch of stuff, among them the Sustainable Development Goals. And here she mentioned quite a few of them, among them number 16 on ocean pollution and fishing zones and other things. And she said that this is one of the goals where EO can be used the most. She also mentioned SDG 16 on peace and injustice and said this is one of the ones where it's currently being used the least. At least that's what my takeaway from her presentation. What types of things can we then solve within these goals? Well, first and foremost, we have illegal fishing. And there is quite a lot of it. And according to some sources, it's up to 19% of all illegal, unreported, and unregulated fishing is actually illegal. So that's quite a lot. And that is estimated to be as much as up to 26 million tons every year. That's a big issue for number 14, life below water, but also number 16, peace and injustice, also our economy. And I think it was last year the UN signed a historical deal, will some say, the so-called 30 by 30 deal, where they said that they would like to protect 30% of all international waters by 2030 in so-called marine protected areas. Here, different things are legal, some of them fishing, some of them diving is illegal. And in order to protect these areas, you need to monitor them, like the ones you have here near the Açores. I hope you can see. I think everyone here and online remembers the Nord Stream incident in September 2022, where someone blew up the Nord Stream pipelines, and this caused a lot of issues for life below water, but also the way we now and then perceive the political landscape. So therefore, it did a lot for injustice. But pipelines like these are not the only critical infrastructure at sea that we are interested in monitoring. We also have wind farms or like these communication cables. These near the Açores, there are a bunch of communication cables. Even if we zoom out, we see there are way more of them. And these are, of course, used for communication, internet, and all of that. If they are cut, we lose internet. Believe it or not, this actually happens once in a while. Especially, I know, near the Faroe Islands, it happens quite often by accident. We have also seen cases where it has happened, what we believe, not by accident. In particular, for the people in the room here, one relevant case is the one that goes from Norway to Svalbard, where these communication cables were cut. In Svalbard, we have a lot of the ground stations for downlinking satellite data. So if these cables are cut, we lose satellite data. So it's quite good to actually monitor these and figure out what is going on near them. And generally speaking, we are also just interested in monitoring huge areas on the ocean, not only for weather forecasts, but also for security-related reasons. Number 16, peace and injustice. All coastal states, they have full sovereignty over their waters, so that means that they need to monitor them, keep them safe and secure. If there are oil spill, they need to remove it. If there are someone in trouble, they need to perform some sort of search and rescue operations. Personally, for me, I'm from Denmark. In Denmark, we need to also monitor the waters around Greenland, which is quite a lot of area to monitor. Up there, we do not have coastal radars or other things to monitor from land. We don't have planes, we don't have people on land, we don't have drones. But we still need to monitor the area. And this leads me to my talk and hands-on session today, where we'll be working on maritime surveillance with satellites and artificial intelligence. And this presentation will be roughly 20-30 minutes on presentation, and then we'll do a little bit of hands-on. Simply put, I find ships. I figure out what they are, who they are, what they're doing, what they're going to do in the future. But more interesting, I find some ships that are doing something somewhere that they're not supposed to do, meaning illegal stuff. That could be illegal fishing. That could be general surveillance over maritime protected areas or in huge areas as near Greenland, or specific monitoring near critical infrastructure. But generally speaking, when you do maritime surveillance, there are different ways to do it and different ways you should think about it. And one of the ways is to do historical analysis. Here you want to say something about what has been going on, what is the quantity of the problem, like what I said in the beginning with all of this illegal fishing. This is a historical analysis. You can also figure out what is the quantity of oil spills or whatnot. When you do historical analysis, you are allowed to use many types of data sources and combine them into one result, or you're allowed to use big-ass models and all of these things. One case is the one you see here, where I've taken a plot from a paper that came out a few days ago in Nature about fishing and general vessel activity. And here they analyze how many of the fishing vessels actually reported what they did. And they found that, for instance, near Africa it's only 22%, near Europe it's 60%, so there are a lot of fishing that is going on that is not being publicly reported, at least. And they did a lot of other analysis as well. And then the other way to do maritime surveillance is to do near real-time analysis. Here, you need to consider your objective, and depending on your objective, you're not allowed to use the same data sources or the same models as you do for historical analysis. For historical analysis, you can take one image of one satellite image, and then wait for a few hours for another satellite image, and then you can combine these results to make some sort of nice analysis. That could be you take one satellite image, and then a while later you get some sort of image from radiometry, and then you combine these results. You cannot do that with near real-time analysis. You can, but that should not be the first thing you do. Likewise, you cannot use the same types of models. For the rest of this presentation, I will talk about some general data sources for maritime surveillance, and then I would actually show you some examples of objects. And hopefully that makes sense when we reach that point why I want to show you objects on the ocean. Let's see. And then we go to the workshop. There is no methodology or theory here, because I hope that the workshop, the notebooks are kind of self-explanatory. And as you probably already noticed, this presentation is a bit different from most of the others, because they focused on a tool set, where here I'm focusing on like a very specific problem. Yes, and we will focus on near real-time analysis. Of course, one of the most well-used data sources for doing maritime surveillance is something that is called automatic identification system data, or just AIS data. And a lot of the times when I say I'm finding vessels, people just say, why don't you go on to maritime traffic and find them there? I can do that, yes. It's not always that good. And for those of you that do not know AIS data, it's just a type of data that most ships should always send out, depending on what type of ship they are. They have information, timestamp, what they're doing, where they're going to be in the future, and all of these different things. So just by monitoring this, you know a lot about what is going on the oceans, actually. But they are not good for monitoring illegal activity. And why is that? Well, AIS can be turned off. simply speaking, you go onto your vessel and you just turn it off, and now you're not emitting the data anymore. Guess what? A lot of the people that are doing illegal stuff turn it off. Sometimes the data that is received by the transmitter is simply speaking not being received from this receiver for different reasons. Sometimes the receiver is not near. Sometimes the signal is simply just not powerful enough, so to say. They can be jammed, it can be spoofed, they can customize their own route such that they say to the AIS data that they're sailing this way, but actually they're sailing there. So the objective in near real-time monitoring is to find these vessels. Yep. So what types of data can you use to do that? Well, you can use free images, freely available satellite images. Some of the most well-used ones are Sentinel-1, Sentinel-2, and generally speaking, SAR data and optical data from free constellations. And this should be the main data source because you want to do surveillance on large areas all the time. You cannot afford, unless you are the American government, to always pay for really expensive satellite data. So you're depending on the free data. And that is like something that always should be running, and then you're detecting something on the free data all the time. And then when you find something of interest, whatever that might be, then you can pay for some commercial images and figure out what is actually going on down there. They can be higher resolution, they can be a different type, whatever. You can also use other types of satellite data, of course. We have the AIS, we have something similar, VMS, NRD, that is, even though a ship, especially in the Arctic where I'm looking at, a ship, even though it's not transmitting AIS data, it is still very interested in knowing whether or not there is an iceberg somewhere. And therefore they use navigation and radars. Now these emit signals that you can actually receive from the satellite, so a lot of ships are still sending out some sort of information that you can find. Yeah, and then of course you also use other data sources. Coastal radars if you have them, and other types. The thought here is that you use as much data as possible. You can't afford to focus on one specific sensor, on one specific satellite, or even one general type of sensors. If you want to do near real-time analysis, you need to combine and do a lot of data fusion. The two, I think, most well-known sources was probably the Sentinel-2 optical data and the Sentinel-1 SAR data. Here I took 1 month worth of images near this island, and it should clearly illustrate some of the issues with optical data. If you want to do near real-time analysis and you would like to trust your data, then generally speaking, optical is not the best. You still use it whenever it's available, but it should never be the main source. On the other hand, SAR data can pretty much always be used. Of course, there are some advantages and disadvantages. The clear advantage from the SAR images is that they can look through clouds when you are here. Up in Greenland, it's dark for extended periods of the year, so it's also pretty neat that it's not dependent on the sun. But there are also some disadvantages. They are more complex to analyze, and even if you just look at it here, you can see the water is sometimes very bright, sometimes dark, and that adds to the complexity. This is due to the scattering of the surface of the water. So it's a bit more complex to analyze. Generally, they have poor resolution, but if you buy commercial data, you can still get really high spatial resolution, but the images are not as good in other sense then. Okay. Some SAR images have very many ships in them. This one have like, I think 500-600. I've seen up to 1,000. If you were to find them by hand, it would take a long time. Trust me, I've made a data set where I did that. It took many hours for one image. It is what it is. Some images have very few images, so ships. Yeah. Many different types of SAR satellites exist, and they all have their own, how can you say, their own purpose and rights. So here we see some different resolutions from different satellites. 4 different resolutions from 3 satellites. Some have a very high resolution, some not as high resolution. But if you want a high resolution, you cannot see a very large footprint. So if you have a SAR satellite with 1 meter resolution, you're probably looking at 20 kilometers, whereas the one down here looks at 250 kilometers. So again, it's a trade-off. For the rest of this presentation and in your workshop as well, we'll be using data from the Sentinel-1 satellite. This is also the satellite that this paper from Nature used. All right. So now we have seen some SAR images. And that leads me to why I want to show some examples of objects on the ocean. Because a SAR image is, due to the way that SAR images are being created, like you get very, very bright signatures from scatters on the ocean. And I have seen both in research but also in industry that the general idea is, okay, if you find some sort of object on the ocean using SAR data, and this object is moving, then it is a ship. And I'm now showing you some examples just to show that that is not the case. So here is our first object. And I mean, of course, a lot of you have not seen SAR images before, but let me just ask you, would you believe this to be a ship? No. Okay, this is actually a ship. And this is one of the best cases of a ship. Like this is the best you can get. Especially if you want to do derived analysis. What about this one? I mean, you can't be right, but let's just guess anyways. Ship? This is a skerry. No, not necessarily. No. What you will see, if you are lucky, is an offset, depending on its orientation, and that is normally what you would use. If you have higher resolution and in different frequency, then you can see the wake. Like if you have X-band, high resolution, you see a wake. This is a skerry. Many places in the world, skerries are well mapped using landmasks. They are not near Greenland. So then you're like, okay, can we do change detection? Yeah, you can. But if you just analyze the picture you had just before, then you would actually see that this moves because of the tidal effects. So you can't even do that. What about this one? Not a platform. This is an ambiguity. So it is, technically speaking, a ship. It's just a copy of the real ship. So can you see this really bright spot on the top? That is the real ship. And then these two thingies down there are copies of the same ship. Due to, simply speaking, you can't have a perfect antenna. There are also side lobes, and if it's a really, really bright ship, the signal can enter the side lobe, and this is what we see here. So copies of the real ship. This is very difficult to say if you do not have the general context of the image. So imagine if I just look at this small subset, then I would be inclined to say this is actually a ship. Especially if I do, let's say, change detection, because there's definitely not a stationary platform there. What about this one? Some of you would definitely know this one. This is also a ship. And this is one of the ones that I'm easiest to see, because this, if you know about SAR data, this is a corner reflector, and it makes it so easy to say that something is going on there. That's a ship. This cannot be a skerry, for instance. This one, a bit more difficult. It's an iceberg. Near Greenland, and here you can actually see quite a few icebergs near. And then I'll just, okay, let's take this one then. Not a ship either. This is also an ambiguity, but a different type.
Here, if you do change detection, you would actually be able to see this because this will show up every 12 days in the same image. But if you take the image just before, just after, it would be gone, and then you'd probably say this is a ship. This one, any guesses? That is a ship, and that is a ship near icebergs. So if you look over there, the dot is like kind of in the middle below. And that we only know because of AIS data. And that was spot on right there, so we know exactly what ship that is. But if you just look at the signature, it'll look very similar to some of the other dots. And that's because, believe it or not, icebergs and ships look very similar up in the Arctic. This one, just a classic natural ocean structure. And that is, as you saw in this video I showed you, sometimes there are very bright structures in the ocean, sometimes they're dark, sometimes these bright structures actually also look like ships. But the thing is, we still use SAR data even though it's so messed up because they can look through clouds and we can use them all the time. It is what it is. Okay. Yes. And then we are going to the workshop. So generally speaking, what you do is you get some sort of data, you apply some sort of model, AI, machine learning, a student assistant, whatever, and then you detect ships. And then after you have found your ships, you can then make some sort of derived analysis. You can estimate the ship type, the ship speed, the ship direction. Sometimes you have 180 ambiguity, sometimes you do not. You can, in some cases, not with SAR data yet, actually estimate the specific ship identity. You can estimate, is it currently doing some sort of military activity? Is it legal activity? What is its future trajectory? And all of these things. But today, I will provide some data to you. And then in the workshop, we will have some models, and then we'll just detect ships. Great. Let's see. So the workshop and data should be available online. The notebooks are available online on the Julia EO here. It's the vessel detection one. If you want to, during the workshop, I will create a model. If you want to train the same type of model, you would also need to download some data from the Google Drive, but you do not need to do it right now because I added a model already that we can use for the later notebooks. Yep.
Can I ask a question?
Of course.
So, in these examples, we basically try to identify whether it's a ship or not based on a single picture. I believe in practice you also include some kind of like previous satellite pictures or like basically the time dimension. And how much does that help and how much does it not help? I mean, something like that you mentioned stories,
Yeah.
they obviously don't move.
Yeah.
But a ship might move and may not move. An iceberg may move, may not move.
See, this is then going back to one of the very first slides I made where I said you need to figure out what is your objective. Now I'll give you two extremes, and then like whatever you might do is probably somewhere in between. One extreme is the historical analysis, where you can add everything you want to, everything. You can add, you can map everything out that should be there, and then you can just make change detection based on that. You can add the time dimension. If it's a specific time of the year, there are probably no icebergs. You can analyze these ambiguities that happen every 12 days, all of that. No issue. Then the other extreme scenario is that you want to, as someone are trying to do right now, you want to do onboard computing on the satellite. Because as it is right now, we actually do not have a lot of data on the ocean. Because simply speaking, it's too power demanding to take images all over and send it down, because if you take 100 images out in the middle of the Atlantic, you see 2 ships. So people just choose not to do it. They try to solve this with onboard computing, where they put the model on the satellite and only send down the subsets where there are ships. In this case, you can add none of that. It's too power demanding, and the model will be too big, and it'll take too much time. And then we have like a spot where definitely you can add historical analysis. You can add. It's very easy to add something that you can put in as input into your model, such as the time dimension. That is very easy. Latitude, longitude, very easy. Putting a landmass into your model is already a bit demanding. So it depends on your need, and especially what you want to. But yes, you can. And it does improve, in some cases, a lot, especially in Greenland. To add these things to your model improves it quite a lot, especially due to icebergs. In my project, we are working with one of Spire's resellers, and so the data is from Spire's satellites, and then so we got it. We got it because it's part of the project that I made at my university with a company called Gatehouse Maritime, and they are a reseller of AIS data. And that's also here. I said a ship ID. Using the AIS data, imagine if you know where all ships in the world are, except the ones that are doing illegal operations, and then you find a ship, and that could only be one of 5 ships from your database, and you know where the other 4 are, then you can say, okay, it's probably that one. Yeah. This is one of the analysis that Gatehouse is doing. Yeah. Yes, so if you have downloaded the workshop, you should have 4 notebooks like this. There is also a data folder. Here there is a small test image from the Sentinel-1 satellite that you can open. On the Google Drive, I have a full Sentinel-1 image if you want to. And the package is, I wouldn't call it either a package or a project, but you can download it on on GitHub here. We have 4 notebooks. In the first notebook, I show how to download data from the Copernicus service in Julia. In the second, we will create a very, very simple deep learning classification method. In this method, we will take these small subsets. As I showed you just before, you can have a subset and then you have something. Is it a ship? Is it not a ship? In the second notebook, we'll train a very simple model to classify whether or not it's a ship, or in this case, an iceberg. We'll go to the data later. In the third notebook, we will then use this trained model to find objects on an image and then classify whether or not it's a ship or not. In this case, actually, ship or iceberg, but I'll come back to that. And then in the final notebook, we'll use another model, a so-called one-stage ship detector that takes an image and immediately say there is a ship, there is a ship, and otherwise it'll do nothing, say nothing for the rest of it. We'll go to it. Okay. So some of the notebooks I will just go through up here, and then you can work on them later. Because, for instance, in this notebook, you can download a Sentinel-1 image. It is not wise if all of you start downloading a Sentinel-1 image right now, so I'll just go through it. And then likewise, in the second notebook, I assume you have the data set from the Google Drive. If you do not, just look up here, and then you can do it later. In the third and the fourth notebook, I have provided the models in this folder that we'll be using. So you can still follow along and actually do the stuff in the third and the fourth notebook. Great. Let's see. In this notebook,
Can you read the text?
yes, I can. Another thing to note is that during the past few days we have seen some examples of really good Julia packages, and yesterday we even got an introduction to how you should make a package. This works. I made it specifically for this workshop, so bear with me. And if I should improve it, I'll most definitely use geostats. Anyhow, so in this notebook, you can just download data, and I actually want to just skip this one initially and then tell you to look at it later, but the reason why I then wanted to go through it anyways is because that I heard that there was someone here that early on tried to download data from Copernicus and Julia, but had issues with it. And that makes a whole lot of sense because a year ago it was very, very difficult. But now it's very simple because of this new service that is called the Copernicus Dataspace. A new service that Copernicus made in November last year. So it's very new. And using it, it's very simple to write APIs or whatnot to download the data. So if you tried earlier to download data from Copernicus and you failed, I just encourage you to try again. And therefore, I just want to show it and see how easy it is. There we have vessel detection. Okay. Here, what we do is we start by asking for some, getting the metadata. Even bigger, of course I can. Damn. Okay. Yeah, so we start by getting some metadata to figure out what exactly we want to download, because sometimes, let's say in this case I'm doing Sentinel-1, but imagine if we did it for Sentinel-2, you would like to know if there are any clouds in the image, so it's pretty neat to download the metadata and filter from it. And we can even illustrate the image before we download it. Here I simply define some parameters, a start time, end time, the satellite, and then I illustrate like just the second image in this data frame to look at it, and then you can download it. And I've downloaded this, and I created the small subsets that is then in the folder. So this is actually the image that we, part of this image we'll find ships in later. Again, this was just to show people that have failed downloading Sentinel data earlier that they should try again. Great, now for the real notebooks. Can you still see it? Okay, great. Great. So in this second notebook, we'll make a ship binary classification. In the notebook, there is some initial theory that you can read if you want to about some binary classification and other stuff. And then we are including the data. We are making the model using flux in Julia, and then we are finding a threshold to determine whether or not we believe that the subset to be a specific object. So I will not go through the theory. You are welcome to do so yourself. I'll just go straight to the dataset. Because if you want to make a model that should be able to take a small subset and say, this is a ship, this is not a ship, or this is a ship, this is ambiguity, this is scary, then you need a whole lot of individual samples, right, from all of these different classes. the data set you have here will only have 2 classes, and therefore I already know that the model that we'll create will be very bad. But the idea is there. This data set I found online. It was created by a Canadian company called Seacore, where they hand-labeled a lot of images with either ships or icebergs. Nothing else. And then we'll take this, and then they made some transformations to the data. In particular, they made something that is called sigma naught calibration, which is, I think, not normal for other computer vision types of problems, but we'll now train a model on these subsets. Here, I'm using the train.json dataset that is online. If you don't have it, that's fine. You can do it later or just follow along up here. Oh yeah, that wasn't the other one. Great. All right. Give me a sec. Okay. So in this set, I have taken the data, I've loaded it, and I created a very simple function to just shuffle and split the data. No augmentation applied or anything. And what we have is then a little bit more than 1,000 training examples and 321 testing examples. Again, it's only either ships or icebergs. So this right here is an iceberg. If it's 1, it's an iceberg. If it's 0, it's a ship. And now we want to create a simple model to train whether or not it's ships or icebergs. Here, I've just, made a real simple function to create a model here. And in this case, we have a simple convolutional neural network that only use convolutional layers and other very simple layers, and then it ends up with just having the last dense layer. Yeah?
The question, so you said you have just classes for ships and iceberg, what about water?
There are no other classes. Later on, I'll argue that this is very bad to do so, because you do not only, there is water on these subsets, but you need something with neither, you need something with different types of objects. But water is actually not the class that is needed, because this is just assuming that you have an object and trying to classify the object. So you will actually never have, when you use such a model here, you will never have a subset with nothing in it. But you might see subsets with other classes than ships or icebergs.
Is the classification for the whole image or per pixel?
This is a classification for these small subsets. Nothing else. In the last notebook, we'll use a model more in line with what you're probably thinking of on the whole image. But not this one. So a very standard way of doing ship classification, ship detection. And when I say standard way, I mean this paper from Nature in January this year and other papers that came out last year, they do ship detection in the following way. They may use whatever, they somehow detect objects. using an object detector. After they have found an object, they take out the subset, which is what you see right here, and then they have a separate classifier where they classify, is this object that I have detected in the first step, is this a ship or an iceberg in this case? In other scenarios, they have more classes, but it still illustrates what a lot of people are doing, even the Nature paper from a few days ago. In the last notebook, we'll use a type of one-stage object detector that works in the full image, that has very many different, is trained on the full image. Yeah. But this is the way that a lot of people are still doing it. So people that are working with deep learning, they're probably thinking, why are you doing it like this? Because people are doing it like this. And I'm just showing you one way of doing it. Does this make sense, kind of?
Just a comment, there are different setups, right? So as explained, there's detection, classification, and segmentation. These are three different machine learning processes. So he's trying to do detection. Someone did the detection, he's doing classification. There's also segmentation where you get each piece of...
If you do detection, you should also, ideally, take into account that it's not a detection.
So when I do, so I'll just go back to the introduction of the 4 notebooks again. And I'll I'll introduce them a bit better, I guess. In the 3rd notebook, we'll make a very classic object detector that especially people within the SAR community is using very often. Then we find objects. This object detector is not in any way saying if it's a ship or something else. It's just saying there's an object on the ocean, due to this notion that you would assume that most bright objects on the ocean are actually ships, so this is what people started using back in the days. And then you take these detected objects and you'll classify whether or not it's a ship or an iceberg. If you are in Greenland, you quite often assume that it's one of the two. But as we saw, there are actually also other false alarms, such as the ambiguities. In this notebook we're in right now, we'll build this classifier. So we will actually not consider detection. We'll only consider classification of this object into either ship or iceberg. Then in the last model, we'll load and use a so-called one-stage object detector. This detector has been trained, granted, not on very many examples, but I trained it on full images such that it also learned what water looks like and other classes. Yeah. Did that help clear up confusion? Some? Great. Great, so we made the model. And this last layer down here, we are simply saying, okay, whatever features we have, squeeze it into 1, and then we are applying a function to just map this into a probability between 1 and 0. In this case, due to our data set, if it's 1, we believe it to be an iceberg. If it's 0, we believe it to be a ship. Again, this is a data set that was used in Greenland, where you assume that these are the two things that you have on the ocean. Great. We'll now define some hyperparameters for this model and a simple loss function, and we can then train our model. And I do not assume that people will sit here and train the full model, so I have done it here, where, let's just put it down here. I have trained the model for like half an hour, and here I've illustrated the accuracy where I assume that the threshold is 50%, meaning that if it's above 50, it's an iceberg, below it's a ship, but that is not the best threshold, but it's just illustrating what we have. So we see that at one point, the accuracy keeps on increasing for the training data, and it doesn't increase for the validation data, and that's where we stop and save our model. This model, from this training, where I have stopped it, where they are not divergent, is the one you have here, the classification model. We now want to find some sort of threshold where we would say if it's above this, it's an iceberg, if it's below, it's a ship. And we do that on the validation data. And then we see that there is some sort of threshold where they have the same recall, if that's what you want to have. And then you can just say, that is our threshold. I've done that. And you can now test your data. Here, we have trained the model to only be able to say whether or not it's a ship or an iceberg. And we have validated on the validation set. Now we want to test it on the testing set and see how good it is. I pick this threshold that I'll be using, and then I just tell it to give me the accuracies. So this is actually not a very good, okay, yeah. So I trained this new model so that I'll get really bad results right here. But let's say I didn't run it again. You would get at this threshold, here, you would have some sort of a similar precision of 90% for both ships and icebergs. So in the next model, in the next notebook, we'll be using this threshold. Just that is the only thing we need from this notebook, actually. Great. Sorry. So now to what we actually want to do. We want to detect ships, in this case, a Sentinel-1 SAR image. And we'll do this in this two-stage ship detector. The first thing we'll do is to load the data, obviously, and unfortunately you can't load a Sentinel-1 image as it is right now in standard Julia and still have all of the metadata. If you can, and there's a package for this, someone please tell me. Yeah? You can load the TIFF file, but you would still want to have the metadata that is not necessarily in it.
It's not inside the file.
So the structure of the...
I think I loaded it once setting up file.
the data looks like... Okay, okay. I would like to see, definitely. That would be neat. I'll see later. Anyways, otherwise you can load it here. This is a small subset of the full image where, why is this so slow? Where you can see that we have a bunch of ships up here. Like I showed in the very first example of different examples, this is pretty much how the ships look like up here as well. But you can also see that the values are very, very high. So depending on what you want to do, you are often normalizing these images differently. If you only want to detect ships, it is actually fine that they are that bright objects are very bright and everything else is dark. But if you also want to detect, let's say, icebergs or oil spills, you would change the distribution of the data. And that is also what this data set did. So as you can see, the histogram, yeah, okay. I'm applying some transformation that the data set also applied. And in this case, in particularly, we have converted to a linear and decibel scale. And this just means that we are changing the distributions. So now the image looks like this. And we can see that there are a bunch of ships in it indeed. And you're probably wondering why we have changed the distribution to go from -30 something to 10. That is a very standard way of changing the distribution of SAR data to make it Gaussian, pretty much. Great. So now we have our image up here. And then, again, the first thing we would like to do is to detect objects. And in this case, we'll be using a rather standard way of detecting objects in SAR data. In fact, I have referenced a paper in this very notebook that is from last year that is using the same method, and also this paper from Nature this year also used a variant of this object detector. Just to say that this is still the one that is being used. Well, a variant of it, but nonetheless. And I have here in the theory, I have another notebook called C5 where I can read about it, but what it is doing is pretty much just to say, okay, for a certain region in the image, we'll figure out, okay, what is the mean intensity, so to say, and if the pixel in the very center has a much, much higher intensity, then it's an object. Very simple. And this is called the constant false alarm rate. You can read about it in this extra notebook. We'll be using this to just find objects. Again, whatever bright pixels you have in the image will be now detected. The classic constant false alarm rate will give roughly, in this case, 53 different objects, and one that is also using morphology will give us 11 different objects. These are highlighted here. This is then the first stage, the object detector. In other computer vision tasks, you also normally use more advanced machine learning for this step. But for SAR, you often use this one. Now, what we'll do now is to take this model that we trained in the in the second notebook, and we'll then apply it to some of these objects to see, okay, do you believe it's a ship? Here we have one of the objects. And this is very similar to the first example I showed you, I reckon. And that's because this is a very classic signature of a ship. We now just want to use our model on this example, and we are now normalizing the pixels to lie between 0 and 1, where they were from -30 to 0. And now we'll see what the model believes. Okay, so there is 0. There is a very, very small probability of this being an iceberg, is what the model is saying right now. And that is very similar to how a lot of people now are finding ships. I had some tasks during the notebook. A lot of them are where I want you to try to change some things. But at the very end here, I have some questions, and we already discussed some of them. Because, of course, there are very many drawbacks to this method. In this data set, we only had ships and icebergs. What happens if I give it an object that it hasn't seen before, such as these ghosts, these ambiguities that I showed in the example? Then it will most probably guess one of them on one of them with a rather high probability. And that is one of the big issues with this method. Yes. That leads me to the final workshop. In the final workshop, we will take the same image, but we will use another type of model. This model is a type of one-stage object detector that will, from the full image, say, okay, maybe I should actually just... It'll take the full image, and it'll divide it into regions that you, when you define your model, define. You can say that every region should be 4 pixels, 5 pixels, 10, 20, 30 pixels. Within each of these regions, you would want the model to, in one step, say, do you think there is an object or not? If you think there is an object, what object is it? If there is an object, what is the size of the object? So in this case, we have ships, a ship there, a ship there, a ship there. We have some cranes, ships. So the model should then say, okay, here we have a ship, a ship, a ship, a ship, a ship, a ship, so on and so forth. Over here we have no objects, and here we have cranes. Now what is then no object? Because if we just look here, of course there are objects. Well, everything that we have not labeled are considered no objects. So if we only label ships in these images, the crane would also be a no object. Whereas if we would label a pier, then a pier would have a separate color. After you have detected the objects, you will estimate its size. But as you see up here, then in this very big ship right here is in many different of these defined pixel sizes. Therefore, many different of these cells would say there is a ship. This is what you see here. So we end up with having several of these estimated sizes. You would then remove the extra ones, and you would end up with something that looks like this. So this is a model that takes one image, and the output will be this. Yes. Someone mentioned the wake earlier. Here we could see what it normally looks like, actually, very zoomed in. Believe it or not, the ship is actually here. And then it's just due to the sharp processing that it appears to be down here. But if you know about this and you can correlate for it, it's not an issue in your later processing. But for all intent and purposes, when you detect ships, you would estimate it to be here and not up here, because it's easier. Great. So now we would load the same Sentinel-1 image, the model, and the text ships with this model. This model was trained with some other transformations. For instance, here we are not doing this linear transformation that I used before. Otherwise, it's very similar. This is then the image. It looks very similar, but with different distributions, and that only depends on what you trained your model on. And this model was trained on images with these distributions. Great. Now we'll load our model. And if you want to, this is this model right here. is in the so-called ONNX format, which is cross-platform. So you can use it in Julia, you could use it in Python, and in very many other languages. And it just works as is, and you can illustrate it online if you want to. In Notebook 2, we made a very simple network, so it was quite easy to just illustrate the different layers. This one is a bit too elaborate to show here, but you can take the model and you can illustrate it on this app if you want to. Up to you. Then we'll simply speaking we'll just find ships by using the model and the image. So now this model has found ships in the image. Here we didn't apply some sort of object detector before. We just gave the full image to the model, and it output this. And as you can see, there are very, very many bounding boxes, and you can see these probabilities are like on top of each other. And that is because I have not applied this so-called non-max suppression to go from this step to this. We could easily do so. And we also see that these scores here are around 80%. And if you are familiar with other, how can you say, examples where you apply some sort of model like this, they are often actually higher. But that's because this model, first and foremost, it's a simple model. It didn't use a whole lot of data to train it. And also the output is a combination of, okay, how sure are you that there is a ship? And how sure are you of this size of the ship? And if you have seen some of these SAR images, you can see that it's not always clear where the border is. And that also reduces this score. Yes. That was actually the introduction and walkthrough of the notebooks. I have made many tasks that I think you could do if you have the notebooks and you want to do it. You can also do something else with it. And otherwise, I'm actually already finished. But that's okay, I guess. I would recommend everyone to just work on these notebooks, look at these tasks I gave you, or drink coffee, or ask questions.
The sensors of the SAR on the satellites are not turned on when they are over the ocean. Is that right?
That is in part correct, right? Yeah. And that is why
they come close to the coast is that they start acquiring data. I remember there was a problem for Açores when people wanted to do inside data because you need almost to ask to turn off the sensor to have data on the islands. Now it's a bit better. Last time for São Jorge crisis, I looked at it, I could get a couple of them. But I only saw data around the islands. So it means large part of the ocean you don't have data for your islands. Is that right?
that is absolutely right. So there are depending on the satellite constellation, of course some people can say, okay, we want pictures from these areas, such as from Sentinel-1. There we have data from these areas near Greenland. So in all of the areas that I'm interested in, at least, we have data. But in the middle of the Atlantic Ocean, currently, there is not any data unless you know that there is something going on. Let's say that you know there is an oil spill, then they take pictures from this area. Otherwise, they do not. And that is because of the power budget and the downlink. But this picture is actually changing. This maritime picture is changing, not because of these historical analysis, but for near real-time analysis, there is this shift in the commercial scene where you can still get pictures in the middle of nowhere as long as you say you want pictures from that area. And you pay it.
And it's a lot.
Yeah.
It's not for
Yeah.
it's not for research.
No, it's not. It's definitely not for research. But I would say, at least for my case, these areas around Denmark, Faroe Islands, and Greenland are well covered by Sentinel and RCM. Quite well. But in the middle of Atlantic, no, not unless you pay.
Another one for curiosity, it's still about the waves. Those very high speed boats that Portuguese and Spanish know that transport very high valued goodies, but they travel very fast. They should leave a good wake. Do you see that? You ever look?
Yeah, I see them, but I mean, we have wakes in 1 in 30 ships we find. It's in this ballpark. But that's also because we're not focusing on these small, high-speed moving ships. So, but yes, they have wakes, but not, as you saw, these ones did not.
I think some time ago, long time ago, I saw someone advertising something, and where you had the SAR, amplitude data with the ship and a very nice wake. And I got the wrong idea that you see wakes everywhere.
It's also dependent on the specific SAR sensor.
Maybe I can also add a little bit. It's also when you have the SAR, it's also very much dependent on the direction of the waves relative to the sensor. So you can have, the waves goes one direction, you can see it, and then if the boat turns 90 degrees, it's much harder.
So earlier, years ago, there was also a lot of research in only finding wakes, because if you find a wake, you assume that it belongs to a ship. But that was when people did these sorts of ship detection methods, where you first find objects and then you estimate, is it a ship or not? Because here you only see this small subset. But in these other models where it's so-called one stage, you train it on the full image. Inherently in the data, when you say there's a ship and there is a wake out of it, it is being used in the model. So wakes are still being used, but not all ships have wakes.
Have we worked in some work with AirCentre where we classified data in some data?
Yeah.
And one of the big problems is that you sometimes have unbalanced stuff.
Yeah.
Much more pixels per your photo than where you And I'm wondering if you also encountered some issues that the cluster not compliance, or what kind of approaches did you approach to avoid some?
The approach we took, simply speaking, it is unbalanced because we will never have as many of these azimuth ambiguities as we will have ships. But sometimes when people train these types of models, they do it on full images. And that leads to highly imbalance between the background and objects. Here we, simply speaking, just cut out a lot of the background. So there is at least a balance between objects and background, but not for the different classes. Yeah.
Is there any false positive issues because weather conditions, atmospheric conditions, like to detect oil spills?
For oil spills?
Yeah.
False positives for oil spills? Yes. Oil spills, for those of you, so ships are very, very bright on SAR images. Oil spills are very dark. And the only reason why they're dark is because in this video that I showed in the presentation, you could see that sometimes the image is dark, sometimes it's bright. That is due to pretty much just the waves and the scattering of the incident radiation. So if you have many waves, it's very bright. If the water is completely still, it's dark. What oil spill is doing is it's lying on the surface of the ocean and makes it so that there are less waves. That is what you observe in SAR data when you observe oil spills. So oil spills is just dark patches. Very many different things are creating dark patches on the ocean. But a lot of these things do not have the same structure. So if you talk about oil spills, we have large oil spills, we have very, very small oil spills. Very small oil spills can honestly look like very many different things. Large oil spills do not. So if you somehow make a model, if we actually see this, maybe if we see this image again, so I don't know. Oh, you can't see it. Down here, it's always dark when I look at it here. And that is because due to the geography of the land, it's always, the surface is always dark. If you do not make some sort of model that has these dark areas, then it will detect everything as dark against a bright ocean as oil spills. But simply, if you include those, it's actually not that difficult because oil has a very specific structure. Algae has the same type of structure, but they are often bright in pictures against a dark surface. So the most difficult thing is actually just to find, get information about where the oil spills are. Yeah. But I wouldn't use the same type of model. This one was making a bounding box. For oil spills, you would like to do segmentation.
Hi, Christian. How do you differentiate the icebergs from the ships? Is just the shape or also the strength of the signal? One are more roundish, something, or less?
You can't use only the strength of the signal. So you are highly dependent on the conditions and the shape. But honestly,
I mean, sometimes visually we understand the difference between two different features.
Yeah.
And then we train models to try to replicate what we see.
Yeah.
But do you see that in the iceberg? Do you understand visually?
No.
Right.
Look,
so the model, so likely the model will also not.
This one right here is a ship. This one down here is an iceberg. This one up here, iceberg, iceberg, iceberg. Why do I say that? Honestly, I do not know. I just know that this one is the only one that had AIS data. And I also know that there are very, very few ships in these waters. It's very rare to have many ships in one of these images near Greenland. And that's why we, when I create my data set at least, say this is a ship. And then you can make some nice graphs that are saying, okay, how good is your accuracy according to the size of the ship? But honestly, if a ship is 20 meters, then it's almost impossible to differentiate between iceberg and ship. Even this one right here, this is a so-called side lobe because of there is a very high wave that is being scattered from the object. if you are in most places in the world, you know almost for sure that they are man-made objects. Icebergs can make the same. So it is very difficult. Huh?
The optical signature of the iceberg, no, before, of course you are using the IES, so you know where they are.
Yeah.
So you can distinguish them between icebergs and ships. But if you don't have that information, you are using, for example, not plastics, but do you understand my question? You can use the optical signatures first?
In Greenland, well, the places where you have icebergs, it's of course dark for parts of the year. When it's not dark and you do have optical images, it's cloudy between 60 and 80% of the time. So, yeah. It's, yeah. And if you're down here, I hope there are no icebergs.
Right.
Yeah. Yes? Perfect. Well done. That's it for me, I guess. Yeah. You're welcome.
Okay, so in 20 minutes we'll have the coffee break ready until 4. So for those who are following online, this is the end of today's workshop. I'll see you tomorrow. For those who are here, you already know, in 20 minutes coffee break and then expert hour here, not upstairs, from 4 to 5. Thank you. See you tomorrow.